In this lesson, we're going to discuss three theorems, but the major goal is the mean value theorem. We're going to start with the intermediate value theorem. This is actually from an earlier part in the text that I chose to bypass so that we could circle around to it here. But the intermediate value theorem says exactly what its name says, which is that you can find intermediate values. So, for example, if we have a function, well, let me give you a supposition first. The supposition is that we have some x values a and b, that being f of a, that being f of b. The intermediate value theorem says if you know your function is continuous, then you're guaranteed that somewhere between a and b, you will hit, if you substitute that value into the function, you'll hit every single value between f of a and f of b. And it just says that there's at least one point where, again, between a and b, you can substitute it in to get all values between f of a and f of b. So for example, if I was to connect this in a very simple way, something like that, then you can clearly see that I've attained all the output values or y values between f of a and f of b. Right? I could draw a function like this. And you might say, well, wait a second, the intermediate value theorem said that they only were talking about values between here. But if you look inside the interval from a to b, you see that every y value between f of a and f of b was accomplished in that interval. Even though, yes, there were some values that were above f of b, well, so what? You've still attained all the y values between f of a and f of b. This has some applications, obviously. Principally, it would allow you, if you knew that, for example, you had a function where f of -3 was -1, and you knew that f of 1, 2, 3, 4, 5, 6 was 4. Then you can immediately conclude, just by knowing f of -3 equals -1 and f of 6 equals 4, you can, just looking at that, say, oh, well, it crossed over from a y value that was negative to a y value that was positive, going from here up to here, which means that it has to have at least one real root between -3 and -6. Right? So no matter how I draw this, I'm guaranteed that I get at least one root or x-intercept. Now, it doesn't tell you that there's only one. One of the practice problems that I'm assigning you will ask you to do that. Prove for a certain function that there is one and only one root between two certain values. So you can get into that, but anyway, that's the statement of the intermediate value theorem. Just think it guarantees the existence of intermediate values. Okay, now we're going to do a little exercise where you are going to put pause. Well, in a second, I should say. You're going to give yourself a little first quadrant graph and put a point down to start, put a point down to end somewhere in your interval, and then connect them any which way you like. So hit pause and do that. Again, you're trying to make a start point and an end point to your function. Doesn't matter where, make a left and a right, could be above, below, whatever. And then you're just going to connect them with a continuous differentiable function. So do that now. Okay, so hopefully you've done that. I'm going to do one up here. The one I'm going to do is, my points will look like this. And if you didn't really understand what I was talking about before when I said draw a function, maybe you should hit pause now. Use the same starting and ending rough points that I've used here. And now, when you hit pause, you'll just connect this any which way you want, making sure that the function is continuous and differentiable. Remember, differentiable means we can't have peaks like that in the middle of the graph because this thing doesn't have a specific tangent line. You can tell it's got all kinds of different graphs or lines that pass through it at that open point. So I'm now going to draw mine, so again you might want to... Okay, so hopefully you've drawn a function between your 2 points. I titled this mean value theorem. This is the thing that we'll be displaying here. So with your 2 points, connect them any way you like. What I'm going to do is connect them like that. It doesn't really matter as long as it's continuous and differentiable. Remember, differentiable shouldn't have peaks in it, and it obviously needs to be a function and to be continuous. You hopefully didn't pick up your pencil, all that kind of thing. So what the mean value theorem says is this. The first thing it does is, well, you can see I've labeled my A and F of A and B and F of B, right? Mean value theorem first says construct a secant line between those 2 points. So the first thing is to find the slope of that secant line, and that will be F of B minus F of A over B minus A. Okay, now the mean value theorem says that if you found that slope, that there are other points, at least one other point, between A and B, such that this is true. So digest that statement for a second and I'll explain it. The basic idea here is this is just the slope of a secant line, right? It's y minus y over x minus x. F prime of c represents the derivative of the function. So what we're saying is that there has to be at least one value between a and b such that there's a derivative that is the exact same as the slope of the secant line. So I'll show you that in blue. On my function, there are 2. Looks like that point right there does the trick, and maybe that point right there. Notice it's not like necessarily the minimum or maximum values. It might be hard. You might have to look pretty hard at this video. But the minimum appears to be where my finger is, whereas the C value, if we want to call this guy C, and this one C, maybe call that one C sub 1 and C sub 2. In these cases, C sub 1 satisfies the condition such that its derivative at that point, the instantaneous rate of change, matches the average rate of change, and this would be the average rate of change, or slope of a secant line. So effectively, that's what the mean value theorem says. That would be akin to, let's say, if you knew that I left the school and I traveled 10 miles in 1 hour, and I traveled to Center City, Philadelphia in 1 hour. If that's the case, then you must be guaranteed that at some moment I was going exactly 10 miles per hour. That might sound very trivial to you, but I didn't have to be going 10 miles an hour for more than one instant. But for example, let's say for part of the trip I was going 5 miles an hour. Well, at some point I'll have to go faster than that to average myself out and give myself an aggregate of 10 miles per hour. So this mean value theorem guarantees that. So this would also allow, if a police officer was at on the interstate, they in theory, they could see where you were, mark your license plate number down, and maybe 10 miles down the road, there's another police officer. They see you, let's say, 5 minutes later, and they realize now, okay, this person has gone 10 miles in only 5 minutes. So that would be 120 miles an hour. And when you passed the first cop, you were only doing 50. When you passed the second cop, you were only doing 50. But they could, in theory again, in mathematical theory, prove that you must have gone 120 miles an hour or more. So you had to have hit 120 miles an hour at least one time for that to be the case. So, there are reaching applications, but the overall thing is here that the average rate of change is equal to, at least at one moment, the instantaneous rate of change. Okay, and then there are, well, just to draw another picture for you, similar, another function that does this. This one right here, here's your average rate of change, there's your matching instantaneous rate of change. You might have connected yours with a linear function. In the linear case, every point, there are infinitely many points that have the same rate of change as does the slope of the secant line because it's linear. Its derivative is constant. Another application of this, if you know that f of a is equal to f of b. So I'm not going to label this as f of a or f of b because they're the same. If you know that that's the case, then you're guaranteed, you think about this being your slope of the secant line, think about your f of b minus f of a over b minus a. Think for a second, what will this be? In this case, f of b minus f of a. Oh, that's going to be 0 over b minus a, which is 0. What that implies is that there must be at least one instant where your function has a derivative of 0. And we already know how important that thing is when your derivative is 0. Those are indications of potential minimum, maximum values, potentially even the absolute minimum or absolute maximum values. So in this case, right smack in the middle, you can see that we would find a maximum value on that interval. This, by the way, is called Rawls' theorem. So Rawls' theorem is a special case of the mean value theorem. So the Rawls' theorem only deals with cases where f of b and f of a are the same, and it guarantees that your derivative will be 0. Whereas the mean value theorem more generally says that your derivative has to be the same as your average rate of change, at least at one moment. You can use this to prove things. You can use these two things coupled with the intermediate value theorem to prove things such as that a function has one root. So for example, if you knew this to be true, that has a negative value here and a positive value here, then that tells you there has to be a root somewhere between, let's say, -2 and -1. Right? There has to be a root somewhere in here. You could use, if you had the equation of the function, you could then use the mean value theorem and Rawls' theorem to establish that potentially there's only one spot where it crosses the x-axis, or maybe 2 or 3, but you could guarantee that if you knew a little bit more about the function, because you could know when it peaks and valleys, etc. So there's actually, I've assigned an exercise to do just that. This theorem is not so important in application as it is in theory, because as I've stated, the fundamental theorem of calculus will be, this is involved in the proof of the fundamental theorem of calculus, which is really awesome. But the basic idea is we need this tool, and you can also understand why someone would want to know this, hopefully. Okay, so thanks very much, and see you later.